I still have my time, yeah.
Yes. You will still have your time.
So I'm in a bit tough position because, as you can see, my long-term co-author, Professor Valery Kharkianin, prominent scientist in the area of theoretical physics and molecular biophysics, died just 4 weeks ago. It's very unexpected. He is from Institute of Physics, and I'm from Institute of Theoretical Physics, but he was a theorist too, and it's of course a very tough loss for us, for collaborators, for all Ukrainian science, and I think not only Ukrainian. Okay. It's a brief content of my talk, and the first 4 items are a brief outline of the concept which Professor Kharkianin intended to expound in his lecture. Unfortunately, it's impossible now. And the 5th is what we can expect from the point of view of molecular self-organization from single molecular reactions. But let's first speak about what I mean behind the term self-organization, because it's a very general term and used in different senses. So I will speak about self-organization in its more classical sense, as proposed by Haken in, for example, his book Synergetics, that is in a synergetic sense, as a phenomenon of threshold-like emergence of new stable stationary states in a system far from thermal equilibrium. And sometimes it's called, this phenomenon called non-equilibrium phase transition. It happens as a rule when some control parameter exceeds certain critical values. It's some conditions, necessary conditions for such kind of phenomena, defined by Haken in particular. So we need, first of all, flow or pumping of some energy or particles or energy of different nature, so on. Input into more or less complex systems with pronounced temporal hierarchy, so it has slow degrees of freedom and fast degrees of freedom. And under these conditions, it's possible to observe so-called dissipative structures, that is, new regimes, new patterns, some ordering. As a rule, when intensity of flow exceeds, for example, reach some critical value, and examples abound of such kind of processes. They are well known, starting from Binar effect, from laser, and many up to societies. One of my colleagues persuaded me sometime that he predicted collapse of the Soviet Union proceeding from synergetic equations as early as in 60s. But we don't go too far, we take another extreme. If we think about a minimal level of complexity, that is macromolecular or especially biomolecules, we may find all the prerequisites of self-organization for working biomolecules or macromolecules. So we have a temporal hierarchy because we have slow structural conformational change and fast, as a rule, fast reaction turnovers. And they interact, so we have obvious feedback and therefore non-linearity. And of course flow, because no one biomolecule, for example, exists to perform only single act. It performs many consecutive acts of binding, unbinding, or transferring, or so on. So this is strange, but only in the early 90s, by us, we are in the world pioneers in exploring such kind of phenomena just for molecules, proceeding from the existence of these main conditions: conformational changeability and presence of the flow, with the possible consequences of self-organization phenomena within a single macromolecule, or even some of its molecular group. Now, it's obvious that such kinds of phenomena are very important, because it's fundamental processes of biochemistry, like binding of ligands, or electron transfer between cofactors embedded in a protein, like in the photosynthetic reaction center, for example. And many possible applications concerning such kind of topics as sensors, drug delivery, and if you have an understanding of this very simple but very complex as for biomolecular processes, then we may have some insight into molecular devices and so on. And to accept that new insight to fundamental biochemical topics like cooperativity or non-Michaelis behavior of enzymes and so on. It's just to remind about, for example, problem of cooperativity. If you have, for example, monomeric enzyme like or transporter like myoglobin, or hemoglobin consisting of 4 subunits, then you have a so-called phenomenon of cooperativity, when saturation with oxygen or some other ligand is, I'm sorry, is standard hyperbolic, for example, for monomeric protein, and with some flexion, and non-Michaelis or non-Muir for hemoglobin. But usually such phenomena is supposed that they obligatorily needs several subunits. We will show that it is not so. For lack of time, I missed it. And I illustrate this with the simplest minimal model of the phenomenon. If you have, for example, 2-reaction states, for example, of charge separation, electron on donor or acceptor embedded in the protein, or enzyme with ligand or without it, this is reaction, forward reaction, backward reaction. And this symbolizes the state of structural subsystems with some potentials. Let it be very simple, for example, harmonic, doesn't matter. Let it be input, backward, forward reaction, like some intensity of flow, and at least one of reaction rate, for example, for recombination or backward reaction, is structurally dependent. This is structural coordinate. Then we have such kind of stochastic problem, and it may be transported to, we may derive it forward equations, evolution equations. And what is interesting, that under the condition of of slowness of structural subsystems, it can be shown that we may proceed with effective Fokker-Planck equation with some non-equilibrium potential governed by the intensity of flow. And after some threshold, it requires, for example, second minimum, we have bistability phenomena and coexistence of two functional regimes. For example, if it is a reaction of some electron transfer and backward recombination, so we have a charge separation in two different regimes and coexistence in some bistability window. Okay. We proceed with this scheme. It is very simple, but rather productive. In our search of processes of electron transfer in photosynthetic reaction centers, that's another long story. But as for experimental evidence, they are quite sophisticated because we proceed from ensemble experiments, and it's never clear because the effect is of hidden nature and very hard to monitor reaction and conformational changes at the same time. But about 20 years ago, maybe, or 15, we have single molecular spectroscopy, and single molecular enzymology. It's one of the first classic example of for enzyme cholesterol oxidase, which can be traced. I'm sorry, I confused buttons. It can be traced by some fluorescent marker, for example, different states of this reaction, for example, oxidized states and reduced states of the active center of the... So we have some kind of random telegraph signal or dichotomic noise, and people then proceed with statistical proceeding of such single molecular trajectories. And one of the first characteristics is called on-time distribution. For two states, as a rule, it has such a kind of dependence. For three states, if you have intermediate, another kind with maximum. Of course, they are all essentially non-exponential. But let's try what we can say if we have a case of self-organization, in our particular case of bistability. Let's proceed with the same reaction, forward reaction initiated by some pumping, and backward reaction with some characteristic dependence. It's the same equations, and we have such kind of system of trajectory which can be simulated by computer, or we may proceed from analytic equations, because it's possible to the systems to transfer to this. We use both methods, and what we find. If we have a system without conformational dependence of the rate constants, we have obviously exponential distribution, time distribution. Or for three states, we have two exponents. And so finally, if we have this dependence, we should proceed from sync equations with some little tricks. It's possible to calculate this quantity in the presence of structural motion. Then we proceeded in this way, and it's simply a comparison between results from analytic equations and from stochastic simulation. After approximately 5,000 flips, we have excellent agreement. This is for some specific parameters, but for all parameters we tested, we have this coincidence. So we are sure that we may proceed from more smooth analytic solutions. And the same is for so-called autocorrelation function. Because this is the second main characteristic for single molecular reaction. This is its analytic expression, and comparison between these two methods even better than practically indiscernible. In our case, we have in our model system such a simple bifurcational diagram. This is the positions of extrema of non-equilibrium potential of extrema of stationary probability distributions, and this is corresponding for some values of parameters corresponding times of recommendation for small pumping and for large, and something in between we have a border value, and this attractor we may call as non-deformed structural non-deformed state and slow recommendation, and this corresponds to the fast. Of course, curves that we obtain are highly non-exponential, but we apply high accuracy method, maximum entropy method of expansion of corresponding on times in spectra. If you have an on time, as for example, such simple systems, as a sum of exponent, then we may simply find the relative populations of different states. We want to see non-deformed and deformed states and the coexistence. If you have a spectrum, then this spectrum consists of several pronounced peaks, and we have then back approximate it with something like this formula again, and find these quantities. And for times less than some value in the center of bistability window, we call it fast, and this for slow, and result is very transparent. This is an example for three values of pumping of the rate of forward reaction, for very small, for large, and something in between. We have, this is close to one phase, and this obviously close to biphasic case. And it's if I scan the percentage of slow and fast fraction with respect to I, to the intensity, I see a very clear picture of initially existed only one state, then coexistence of two states, and then disappearance of the initial, existence of non-deformed, for example, state, and absence of deformed, and vice versa at large values with bistability window. For ACF, for correlation functions, the picture is even more eloquent, I would say. This is correlation, examples of correlation functions, again, for small, for large values, and in between we see drastic difference, and a sharp tweak in the bistability window of correlation. It perfectly corresponds to the general general notion of phase transition. Very big portion of long time component. So maybe I'm going to finish, and conclusions are very simple. To my surprise, to our surprise to some extent, we discovered that such sort of phenomena as this example of molecular self-organization can be comparatively easily traced by careful processing of experimental trajectories from single molecular reaction, just in the primary characteristic, because people explore four-time correlations, for example, in a more complex model, and analyze this non-exponentiality ad infinitum, but there's no traces of new mechanism. We, of course, can make models of some hierarchical process clusterization with these Mittag-Leffler functions and subdiffusion, superdiffusion, and so on. It's a fascinating topic, but this phenomenon is very simple and transparent. And here, I would like to...
Open for questions.
Okay, I have one question relating to time, because you are giving time also here in seconds.
Yeah.
How can you explain us? What is really means?
These are the parameters which we employed when described photosynthetic reaction centers.
Okay.
In this case, this is real time, but we unfortunately, we have no experiments on reaction centers, single molecule experiment. We have only ensemble. And moreover, I don't know for the time being experiments in literature when scanning with concentration or with intensity of, for example, of input of some actinic light or so on, are conducted, because people don't know what to search, what to find.
Exactly.
And this is very transparent guidelines. If we were able to perform single molecular reaction center experiment, it will be brilliant proof of this concept, because we have many evidence from ensemble experiments. But you see, people who don't want to believe, they always say, oh, this is indirect proof, and single molecules will be more straightforward. So I have no time to tell about photosynthesis and such kind of phenomenon reactions. That's very interesting, but it takes, unfortunately, Professor Harkin had lecture, but alas.
Thank you.
Are there any other questions?
Of course, your talk was very interesting, but maybe I ask a forbidden question. Where it can be seen, or where you see nanomaterial sizes, not dimensions?
Nanomaterials of what? Which dimension?
I don't know what, but
no.
But where is nano dimension, nano size?
I'm sorry. I think that biomolecules, molecular systems are true nanosystems because you have tens of angstroms.
This is not the size.
It depends what you speak. What you call nanosystems.
Maybe okay. Okay. Same
It's very broad.
Same view.
Okay, since that we are running late, we thanks Professor Christophorov once again.